Okay, welcome back. We were discussing the stereoelectronic effects or stereoelectronic requirements for substitution and elimination reactions. Okay, but we will take some real examples and we will discuss mostly on the aspect of conformation and reactivity, because all these things are coming under dynamic stereochemistry, that is conformation and reactivity, and we will discuss the reactivity of cyclohexanes towards substitution and elimination and different examples. Okay. Now, if we take a cyclohexane, suppose this is 4 tertiary butyl and cyclohexane with a substituent with a Levy group at C1. Okay. Now, this can exist in 2 diastereomeric forms. One is the cis isomer, another is the trans isomer. Okay. So, this is the cis trans. Remember, the T butyl group is there, so that the conformations are locked. If this is not there, then they will become conformation, they can flip to each other. Okay. We want to study the behavior of these towards substitution reactions. Okay. Now, there are different kinds of mechanism for substitution reactions. Suppose we do it under conditions which favor SN1, under SN1 conditions, and this one also subjected to the same SN1 conditions. So, if it is SN1, that means there will be formation of the cation, and this is the first step in SN1 reaction. It is the same cation that is generated here. Okay, same cation that is generated here. Now, what happens here, which one will then react at a faster rate? There are again you can think in 2 ways. One is that when X leaves in this system, there was, if X is quite big, say a tosyl group, if X is a tosyl OTS, then that is quite big group. So, when X leaves, that leads to the release of the steric compression that it was having, this 1,3 diaxial interaction in the form of 1,3 diaxial interaction. So, that is released when X departs, whereas here X, when X departs, that will not be the case. The other thing you can other way you can think of, that the energy level of this, the axial compound, the axial X will be higher than the energy of the equatorial X, and if the carbocation, that is same in both the cases, is here, if it is the cation, then what happens, it will be easier for, there will be less energy requirement for the axial X to be converted to the cation than the equatorial X to be converted to the cation. So, the axial isomer will react at a faster rate than the equatorial isomer because of this. If you remember, if you carry it under the SN1 condition. Okay. Ionization is favored in case of the axial. Either you can say that the release of this 1,3 diaxial strain, or you can also draw this energy, the energy diagram to show the relative ease of the axial substituted compound over the equatorial substituted compound in forming the cation. Less energy is required. Okay. Now, if you now do the same reaction under SN2 condition. So, I add Y minus and here Y minus. In the first case, I did not add the nucleophile because it was SN1. So, anyway, whatever nucleophile you add, that is the very fast step, that step. So, there will be formation of both axial and equatorial products there. Okay. So, what I am saying, that when the cation is, the carbocation is formed, because the next step is very fast, so the nucleophile can attack from both sides, but there may be some discrimination, equatorial product may be a little bit more, but in theory, because the product is very fast, so there should not be any selectivity in this attack in SN1 conditions. Okay. Whereas, in SN2 now you have the requirement of the Y minus should approach and attack from the back side of CX. That is number 1, and number 2 is the transition state involves involves a carbon, maybe the carbon which is being attacked, that is transformed from sp3 to a trigonal bipyramid structure. That means, what happens when Y minus, take the simple SN2 reaction. So, in the transition state what happens, you have, this is suppose X delta minus and this is Y, that is your nucleophile, and the 3 groups that are there. So, this is the transition state, trigonal bipyramid, okay, sp2 hybridized carbon, but since both are holding X and Y, and not very tightly but loosely, because the bonds are now more or less half, this is half broken and this is half formed. So, the transition state is a bipyramidal transition state. So, the same thing will happen here. So, the transition state will look like this. See, these 3 groups will be, these 3 groups resemble these 3 bonds. So, these 3 bonds will be in the plane, and here it will be Y delta minus and here it will be X delta minus. Okay. And in this case what will happen, X, here it is X delta minus and Y delta minus, and then the final product, here the final product is, sorry, put the T butyl, the final product is Y in the equatorial position, because we are replacing the X which was axial, and because it is SN2. So, there will be inversion of configuration, and that exactly what happened, and in this case the product will be the axial one. Okay. Now, the question is which one will react at a faster rate. That depends on the relative size of X and Y, the relative size of X and Y. Okay. If Y is big, if Y is bigger than, if the size of Y, so we are saying Y is bigger than X, then what happens? If Y is bigger than X, then this transition state will be less stable, and this transition state will be more stable. Okay. So, if that be the case, then we can say that the axial tosyl will react at a faster rate than the equatorial tosyl, and in fact, a reaction has been done where Y is, but remember Y has to be bigger than X. So, X was suppose chlorine, here that was not tosyl, X was chlorine or maybe bromine, you can also tolerate bromine, and you are replacing it with your Y minus is SPH minus, suppose, which is quite big, thiophenoxide. Okay. So, if you do that, so now this is your Y, so Y is bigger than your X. So, what was actually reported that this reacts about 60 times faster, this reacts about 60 times faster, but the number is not very important. The important thing is that the concept, that why this reacts faster than this, because of the size of the nucleophile is bigger than the size of the leaving group. So, now in the case that will cause destabilization of the transition state obtained from the equatorial bromide. Okay. I hope this is clear. The next is, so this is, so we have discussed SN1 first and then we have discussed the SN2. In both the cases you see the axial isomer is reacting at a faster rate, of course, provided that size requirement was there, no, in this SN2 case, that the nucleophile has to be larger than the leaving group. But so if that be the case, in both the cases, the SN1 case or the SN2 case, the axial is reacting at a faster rate. Okay. In case of see, there are reactions which are called reactions which go via allylic rearrangement. That means, if you have a leaving group here and an allyl system, and if you add the nucleophile can attack this carbon, and then the process can go in this way. So, Y is attached, it is not directly attacking the carbon bearing the leaving group, it is attacking the end carbon of the double bond, okay, the allylic carbon of the double bond or the gamma carbon of the double bond. Okay. Then, so what is happening? This is Y and the product is this. Okay. This is what is the this is called SN2 prime. This is prime, that means SN2, but it is not attacking the same carbon as the which is contains the leaving group, it attacks another carbon. So, that is why this is SN2 prime, not direct SN2. Okay. In SN2 prime, in cyclic systems, see, if you have a cyclohexane kind of thing, I am sorry, let us see, if you have a cyclohexane and you have a leaving group here, OCO, say AR, a leaving group, and acetate, a benzoate kind of thing, leaving group, and a group R here. Okay. So, now the nucleophile, whatever nucleophile you have, will attack in an SN2 prime fashion. So, it attacks here, it goes there and that goes out. Okay. Now, the question is from which side it should attack, from which side it should attack. In direct SN2, it should attack from the opposite side of the benzoate, okay, the leaving group. In SN2 prime, the nucleophile is the other way around, the nucleophile attacks from the same side of the leaving group, from the same side of the leaving group. Now, you can say why is that? That means, I am saying the nucleophile should attack from the beta phase. Okay. Why beta phase? Because this is the leaving group is also in the beta phase. Okay. Now, the question is why? The answer you can simply answer without writing any confirmation. You can say that if the nucleophile attacks from the top phase, then the negative charge that will be formed here will be in the bottom phase, and that negative charge now will be anti to the will be anti to this OCOPH. So, it will be easier for that negative charge to come back and kick out the benzoate. Again I repeat, this appears from the beta phase because the negative charge that will be generated here will be in the alpha phase, and then that alpha phase negative charge, for the alpha phase negative charge will have easier elimination of the benzoate. The alpha phase negative charge can easily displace the beta benzoate, okay, because they are anti to each other. On the other hand, if it approaches from the alpha phase, then the negative charge is formed in this side, and now it will be difficult because they are on the same side. Okay. So, there will be difficulty in kicking out the benzoate because they are on the same phase and they are both having the negative charge. See, this is you are trying to generate a negative charge in the same phase as the negative charge itself where it is generated. Okay. If you want to go to the conformational level, so what I have said that if the nucleophile, without going into the conformation, you can say that if the nucleophile approaches from the beta phase, then the double bond is here. So, initially that means the negative charge that is generated will be in the alpha phase, okay, and then this is beta. So, it will be now, it is like a trans elimination, as I said in the case of E2 elimination, it is kind of a trans anti elimination, the same thing here, that this comes out, this comes back and this goes out. So, there will be, it is much, it will be good that if they have anti relationship. Okay. So, this is without going into the detailed conformation analysis, but you can do a quick conformation analysis by drawing the cyclohexane, you know, that is drawn in the half chair conformation. So, you can, without going into any complication, I will just show you one approach of how to really draw the conformation and make this thing look the actual, go into the actual conformation analysis of this SN2 prime reaction. See, this is kind of not correct because you are using a plain hexagonal cyclohexane, but that is not the correct. It is actually the cyclohexane has this type of conformation. So, now what happens, where is your acid, the benzoate? The benzoate is here, OCOAR. Okay, actually, see, in cyclohexane these groups are pseudoaxial and pseudoequatorial. Okay. So, here the group will be up, and so this will be pseudoaxial OCOAR, and this will be hydrogen, and here there will be the pseudoaxial hydrogen, and here this will be pseudoequatorial hydrogen. Okay. Now, let us actually drop these two bonds just to make it less complicated, because we are only concerned about this carbon, that carbon, and these two olefinic carbons. Okay. Now, the nucleophile can approach from the, because this is beta. So, I said the nucleophile has to approach from the top. Okay. So, if it approaches, it has to approach from the top. So, if it approaches now, so what will happen? This will, see, this will change, this will become a cyclohexane system. Interestingly, now you are dealing with a cyclohexane system, as there is connection between the nucleophile and this double bonded carbon. So, this will now form, see, this carbon will little bit push up as the nucleophile comes here. So, as if there are positive interactions. So, this carbon is going up. So, if carbon is going up, that means you will get what is called a chair like transition state. See, this is the nucleophile, this is the HA. I am showing these two, I will tell you the reason why I am showing this HA and HE, although they are not participating any in the reaction. Now, you have a negative charge here, okay, and you have OCOCH3. So, now the negative charge, and actually you have a R group to start with. Where was that R? The R was the beta. So, R was here, okay, and so the R was now here. Remember, it was on the back side. So, R was, this part is in the back side. So, R is here. So, now this comes and kicks out the acetate, and the product is the cyclohexane again, but the product will, if you draw it in the chair form. So, you have a double bond here, you have R here, and you have nucleophile here. So, the important thing is this R and nucleophile will be cis to each other, and there is a chair like transition state. And this attack is what is called an anti-parallel attack. Anti-parallel attack, because this is based on the relationship of the attack with the axial hydrogen on this side, okay, on the axial hydrogen on this carbon. So, because the axial hydrogen is alpha, so pseudoaxial, so the nucleophile is approaching from the opposite direction. So, this is called anti-parallel attack. If the attack takes place from this side, that will be called parallel attack, but this cannot happen because the stereoelectronic requirement says that this has to come from the same phase as the benzoate. Okay. So, this is one way of doing. There are other, see, there will be anti-parallel attack also, but that cannot involve this type of cyclohexane. You have to flip it and then do it. Okay. But we are not going into, because this is a foundation course. So, we are not going into that detail, but remember that the way I drew the chair, because I know that in the chair form, when you write a chair form, these carbons and these carbons are both above this, above the plane, horizontal plane containing this carbon. So, when I brought the nucleophile, I know that this is going to go up, that means there is already a carbon up and this is up. So, that gives you a chair. If the nucleophile if the nucleophile attacked from this side, which is not happening in this case, but that will go through a, even if that happens, so this carbon will go downwards, and in the half chair in the twist boat conformation, this is what is the geometry of a twist boat. So, in the parallel attack, there will be the formation of the twist boat, because that is going down. So, you remember these things, that will be useful in your future courses when you take an advanced stereochemistry course. Okay. Because again I tell you, stereochemistry is nothing but visualization of the 3D molecules. So, this is one case where students get stuck, that why it is a, how do I know that it is going through a chair conformation? I said that in the chair, study the chair conformation, that these two carbons are above this carbon if you take a horizontal plane. So, that is what is happening. This is your horizontal plane, this is this carbon, and this is going up. Okay. So, that type of tricks you have to have in your mind, so that will enable you to draw this type of structures. Okay. So, the stereoelectronic requirement for SN2 prime is that the attacking group, the nucleophile, should be coming from the same side of the leaving group. Okay. So, that takes care of the SN, the substitution, nucleophilic substitution reactions in cyclohexane. Let us now take the elimination aspect and do some problems. Okay. First problem, let us try to do. There are this type of questions can be given, that suppose you have this compound, a cyclohexane substituted, tri-substituted cyclohexane. This is what is called methyl chloride. You have heard of menthol, a natural product, methyl chloride, which gives anesthetic sensation. This methyl chloride has this type of configuration. There is another compound which is very similar, but only the chlorine is alpha. Here the isopropyl is alpha, chlorine is beta, methyl is beta. You have another compound where chlorine is alpha as well as isopropyl, but the methyl remains beta. This is called isomethyl chloride. Okay. Now, if you want to do dehydrohalogenation, see base, okay, you want to replace HCl, dehydrohalogenation minus HCl by a base. Question is which one reacts faster, or which one reacts faster, or there may be some problem with some molecule, or which molecule has that problem. So, in order to solve this type of problem, this is the reactivity, that means which reacts faster, that is which reacts faster. So, how do you answer this type of question? You draw the conformation, the correct chair form of this molecule. So, where is your isopropyl? You see the isopropyl is alpha, is having an alpha orientation. Now, you have lot of flexibility. See, alpha you can put anywhere, see, but you have to see you have to pick up the correct bond, either equatorial or axial. Now, to start with, since this is a big group, so I will try to put it in the alpha as well as in the equatorial position. So, my best bet is that I put this here. Okay. If I put that there, then the next is chlorine. Chlorine is beta, that means chlorine is also equatorial, and then the methyl after one carbon. So, the methyl is also beta. So, this is the preferred conformation, because if you flip it, you will get all this as, so the methyl is here now, axial, the chlorine is here, axial, and the isopropyl is here, that is also axial. So, unstable. Okay. On the other hand, if you write the conformation of this, So, this will be again isopropyl I put in the alpha equatorial position, then the chlorine now it is alpha. So, it will be axial and now the methyl remains in the equatorial position. If you flip it, now there is no requirement of flipping, because this has got an axial chlorine, and that means you have to check whether it has got any hydrogen which can eliminate axial hydrogen. Yes, there are two sets of axial hydrogens which can be eliminated. So, either this can be eliminated, this HCl, or this can be eliminated. So, basically you get two products, one is this one, this is isopropyl, this is the isopropyl and this is the methyl. Of course, here alpha beta it is not in the chair form. So, you can convert it into the, write it in the cyclohexane. So, double bond, this is isopropyl and this is your methyl, that is one product, and the other product is on this side. So, other product will be isopropyl remains and the double bond is here and the methyl is here. So, these are the two products, a mixture of two products, but elimination will be facile because the chlorine is occupying an axial position and there are hydrogens opposite to it. On the other hand, this molecule has a problem. This molecule in the preferred conformation is this one, where the chlorine is equatorial and all other substituents are equatorial. Now, in order to have dehydrohalogenation, this molecule has to flip, but that requires enormous energy, because you not only make chlorine here, if chlorine is axial, if you flip it, then chlorine becomes axial, and yes, you have a hydrogen here which is anti to it. First of all, it requires much more higher temperature to do this dehydrohalogenation reaction, that is number one. And number two, the difference with this is that it can only give one product, the double bond can only be here, that means it only gives this product and not the other one, because other place the hydrogen is equatorial, it is not anti-transdiaxial to the it is not having a transdiaxial relationship. Okay. So, there are two things. First of all, this reacts very sluggishly. If you want to do dehydrohalogenation, you have to heat it up, and then the other difference is that it can only give this product, and this product cannot be obtained from that, because there is no anti-hydrogen in this case. Okay. So, that is one interesting problem, methyl chloride and isomethyl chloride. Okay. Let me see. Another interesting example is dehydrohalogenation of this compound. Okay. Dehydrohalogenation of this compound. This will never undergo dehydrohalogenation. Why? Because if you draw the preferred conformation, so you have alternate alpha and equatorial alpha and beta chlorines, but the interesting part is all the chlorines are in the should be in the equatorial position. That should be the most favored conformation. Okay. So, there is no question of any elimination here, because the chlorine is not occupying any axial orientation. If you flip it by applying energy, thermal energy, yes, it will flip, but the problem is it requires lot of energy, that is one, and the other problem is even if you flip it, you see there is still no axial hydrogen adjacent to the chlorine. Okay. All the hydrogens are now equatorial. So, you do not have any situation where there is hydrogen and chlorine which are transdiaxial. So, it cannot eliminate. So, elimination is not possible, means elimination not possible. I am talking about dehydrohalogenation. Okay. I am talking about dehydrohalogenation. So, this is interesting. So many chlorines are there, but it cannot eliminate, simply because in the ground state it is in the ground state it exists in this all equatorial conformation. If you heat it strongly, it will go to the diaxial, but still that is not capable of doing any elimination, as no hydrogen is anti to the chlorine. Okay. Let us do just one more example of where bond migration, see where rearrangement reactions in cyclohexanes, rearrangement in cyclohexanes. Now, suppose you take no tertiary butyl, suppose you take cis 1 amino or 2 amino, I do not know which one is 2 amino 1 cyclohexanol. Okay. If it is cis, then basically what you have, you draw the cis compound OH and NH2. So, OH will both are beta because it is cis. So, if both are beta, then one has to be axial, another has to be equatorial. Okay. Now, you know that it is like if you add HNO2 in this system. So, this will be converted into a diazo group, and that will be this compound, and it is very similar to what is known as pinacol rearrangement, that in pinacol rearrangement you have OH and OH, and the moment you make OH2 plus here, this goes out and one of the group migrates here. Okay. Now, group that migrates, again like elimination, here again in cyclohexane system, that is true for here also, the group that migrates should migrate the group that is anti to it, or the bond that migrates should be anti to the carbon diazonium bond. Okay. So, now in this case you have to look that if the nitrogen leaves, this bond is broken. So, what is anti to it? You can see the anti bonds of this is that one, and also of course, this one also. These two are the anti bonds to this nitrogen. So, in theory both can migrate, either this can migrate and this leaves, or this can migrate and this leaves, but resulting in ring contraction. There will be a contraction in ring. However, in reality only this migrates and that goes out. Why this migrates? Because the cation that is generated is stabilized by the oxygen. So, this does not migrate because there is no assisting group to help the cation to be stabilized. So, this migrates and what you get is this compound. This will be the cation, and finally, a proton is lost and you get cyclopentane aldehyde. Okay. Now, this is one conformation of cis aminocyclohexanol. There is another, if you flip it, you get another conformation, and in that conformation this OH will be equatorial and NH2 will be axial. Okay. Now, you see the difference. If you treat that the same thing, because you are treating the same thing with HNO2. So, HNO2 will make the amine the diazonium. So, that will be N2 plus, and this will be OH, but now you have a hydrogen, the CH bond which is anti to the carbon nitrogen bond. So, this hydrogen will now migrate, is in a position to migrate, because it fulfills that stereoelectronic requirement that the migrating group should have the bond which is anti to the bond that is being broken, that is leaving, with the bond which is containing the leaving group. So, this leaves now. So, resulting in OH and this is plus. So, that is nothing but cyclohexanone. Sorry, that is nothing but cyclohexanone. Okay. So, in one case you get cyclopentene aldehyde and in the other case what you get is a cyclohexanone. So, ultimately you will get a mixture of the two, because there is hardly any energy difference between these two conformations, because their steric bulk is more or less very similar, and in both the cases one is equatorial and the other is axial. Okay. So, I think that is the type of one. We have rearrangement reaction we have discussed in cyclohexane, and there are a lot of problems that can be generated from this type of pinacol-pinacolone type of rearrangement, okay, or epoxide formation. So, those will be given in the assignment when we give the assignment, when you attend this online course. Okay. Thank you.